Hello. In our last video, we looked at how we could use Bode's rule to easily plot frequency response, and also we looked at how we could identify poles at nodes. Then we talked about a situation where it would be difficult to get a capacitance from the node to the ground in such a circuit. So Miller's theory would help us split this capacitor into two. So the same effect, we have one which goes from the node to ground, and another one which will go from this other side to the ground. So we could get the poles at this node and the poles at this node easily. Let's try and look at how Miller's theory helps us solve this problem. Assuming we had any impedance, not only capacitance, from a node to another node where the voltages are changing, that's very important. The two nodes should have their voltages changing, so this cannot be grounded. If this is grounded or any of them is grounded, then this theory wouldn't apply. So if we have two nodes here, node 1 and node 2, with the voltage at node 1 and node 2 being V1 and V2 respectively, then we could replace it with two different impedances, one moving from node 1 to the ground, so we are going to call that Z1, and another moving from node 2 to the ground, which we will call Z2. Okay, now assuming we have the same current flowing from this node to the impedance being the same as this current, then the circuit would not know that we made these changes. Once the voltages and the currents are the same, that is all electrical circuits are interested in. In this case, if we split the node into this form, then the current through this node would be equal to V1 over Z1. And that should also be the same as the current that was flowing through the node originally. And originally we had the current being the voltage V1 minus V2 voltage here, all divided by the original impedance ZF. So zooming into this side, okay, then we just have to make Z1 the subject, then we have our equivalent circuit. In making Z1 the subject, we can rewrite the equation this way. V1 over V1 minus V2 all times ZF will be equal to Z1. So all I did was change position of Z1 in this numerator, and I multiply both sides by ZF. Okay, then I can divide both sides in the top and the numerator and the denominator of the factor in the bracket by V1, and I'm going to get ZF 1 over V1 over V1, which will be 1 minus V2 over V1, which is going to be the ZF. Okay, sorry, Z1. So if we wanted to find that of Z2, we could do the same calculation, or a simple way is just interchange the position of V1 and V2. Then we could see that Z2 here would be equal to ZF 1 over 1 minus, so this time I would write V1 over V2, and this is going to be ZF 1 over 1 minus V2 over V1. Okay, so we can look at something here. Assuming we had an input voltage here just as we did before. So assuming we call this side the input and we call this side the output, then our V1 is the input voltage, our V2 is the output voltage. Then we can modify our formula and call this the gain. Then the formula becomes Z1 is equal to the original impedance given 1 minus the gain. Then for Z2, that's the impedance at the other side of the node, or at the other node, becomes the original impedance ZF 1 over 1 minus 1 over the gain. Okay. The next thing is we try to replace this with the capacitor that we had. So instead of an impedance, I'm going to replace it with a capacitive impedance or reactance. And in that case, assuming I had the original capacitor here, ZF, and I wanted to redraw the circuit like this, RS over the new Z at the input, so I call this Z1, and then I have my RD here, and the new at the other part Z2, C2, which is grounded. So I can find the poles at these two nodes in this case. So what would be the value of C1 and what would be the value of C2? So if we had our original being 1 over the impedance, which is SCF, then we are going to have 1 over 1 minus 1 over gain, and we have our impedance of the capacitor at the other node being SC2. So what we do see is, in terms of capacitance, we are seeing that the capacitance itself is just multiplied by this factor here. Now similarly, we could also write it like this: C1 is equal to 1 over the original capacitive reactance, which is an impedance. Yes, but in terms of capacitance alone, we can clearly see that on the left hand side, we can say the capacitance C1 has become the original capacitance in the feedback, which has been boosted by a factor of 1 minus the gain. And on the right hand side, you can see that the capacitance alone, not looking at the impedance, is the original capacitance, which has been boosted by a gain of a factor of 1 minus 1 over the gain. So assuming the gain in the common emitter stage is GMRD, negative GMRD, then we can rewrite the whole thing as this. We had our RS here, then we also had our so now the new capacitance has been, instead of C1, let me write C1 is equal to the original CF 1 minus, so the gain now becomes minus GMRD, which becomes 1 plus GMRD. Then we have our other side of the capacitance also given by C2, which is equal to the original feedback capacitance 1 plus 1 over GMRD. So can we get the poles at the two nodes? So let's call this node 1 and call this node 2. So from node 1, if we set the input to 0, what resistance do we see from node 1 to the ground? we see some here, we see another resistance here, but the resistance here is infinity, assuming at low frequency, which is a good approximation to make, even though this time around we cannot always assume low frequency, since we are taking frequency into consideration when we are doing frequency response. But let's just assume the frequency is not high enough to change the capacitance value here to get a proper impedance. So we still assume infinity here. Then the resistance seen from ground will be Rs times okay, so the pole will be, so this is pole 1 at will be the resistance seen from ground, which is Rs, and the capacitance is Cf1 plus GMRD. So the first thing we notice here is that the capacitance has been boosted, which is somehow called the Miller effect. So indirectly we know that capacitance, as we have seen now, if they are shunted, or a capacitor that connects to the ground this way, always reduces the speed of the circuit. And if we had the original Cf, like 1 over Rs Cf, then our bandwidth would have been somewhere here. So from both this plot, the low frequency gain GMRD, and assuming we just had 1 over Rs Cf, then our 3 decibel minus 3 decibel bandwidth would be up to this point before it reduces by minus 20 decibel per decade. By this time, Miller's effect means that the input capacitance has increased, and it means that this term will now go further because we are increasing the denominator by a factor of 1 plus GMRD. We are going to have 1 over Rs Cf, which is boosted by 1 plus GMRD, and that means that our bandwidth will be reduced. So by bandwidth, I mean the effective frequency range where the gain is not reducing. Okay, so I hope you found this video useful. See you in the next video. Bye.